Hello, how's everybody doing? We're going to bring this session online. I'm Matthew Johnson-Robertson. I am a field roboticist myself. I'm very excited to be here. We have a great array of speakers. I'm looking forward to hearing about where field robotics is going. I'll do a 1-minute intro on field robotics. That is what got me into robotics. I think field robotics is, in my humble opinion, the hardest kind of robotics to do because you got to be on a boat or in an airplane or in the desert, and you still got to get your papers out, and you can't run your experiments over and over again in Gazebo. And so I think we need to continue to support this subfield. I think it really teaches people what they need to do to get a real robot to work in a real scenario. And I'm so excited to hear about the future of field robotics from these really great speakers. So our first speaker coming up to the stage is Margarita Chli. She's from the University of Cyprus and ETH Zurich, and she's going to tell us about some flying robots.
Okay. So yeah, maybe you should know that the topic was given to us. So I was a little bit surprised to be invited to give a talk about field robotics. And then I was trying to figure out what to say. I asked ChatGPT what field robotics is supposed to mean. And we came up with an explanation that I thought I could roll with that. So it was about being able to do robotics in unstructured environments, in complex scenarios. So hi, everyone. My name is Margarita Chli. And I've been working on vision-based robotic perception for some time. And yeah, the topic of today is, are we ready? Is the field of vision-based robotic perception ready for field robotics? And you might say, oh, this conference is full of works doing vision-based robotic perception out in the fields. And yeah, that's how it works. Great. And here's one example. So I guess some of you know this video. This is a clip from a promo video from Skydio that it's showing how a drone, a Skydio drone, can follow you while you're doing your favorite sport. It's using a set of onboard stereo cameras, analyzing some data onboard, offboard, and figuring out where you are such that it can really follow you around while you're doing your thing. So you might say, there we go. We have vision-based robotic perception that is able to go out in the wild in unstructured, complex environments and do something useful. So are we there yet? Is that all there is? And to answer to this question, I wanted to take you to a journey around a timeline of vision-based robotic perception, my timeline. So outlining some events that for me were milestone events in pushing the field forward. So first of all, 2011, Fukushima disaster. I argue that we had robots able to play the violin, but not sufficient autonomy, and definitely not enough vision-based robotic perception to enable this autonomy for robots to go out there and do something helpful when we really, really needed it. And this was an inspiration to me, and I guess to many of us in this room, and many, many proposals have come across since then and already now. 2012, now this is an ancient video for some of you. This is the first time we demonstrated that autonomous flight of a small unmanned aerial vehicle is possible using one camera and one IMU. So this is running a PTAM in the background, plus IMU feeds, and using velocity commands to showcase some autonomy. But of course, in order to capture a video like this, we needed to do a lot of choreography beforehand, right? In order to capture these 2 minutes of autonomy, there was a lot of choreography and have my sensors initialized properly, the system initialized properly, right? Then 2018, there's this article in Science Robotics about the 10 grand challenges in robotics. So people have started talking about these problems, have been talking about these problems for a few years. So, and I outlined there some challenges like robot swarms, navigation and exploration in extreme environments, AI for robotics. Then 2019, we demonstrated with my team the first collaborative monocular SLAM for a small UAV swarm. The drones take off, they know nothing about each other, they exchange information via a central server, and that's how they collaborate to build a map of what it is that they're looking at. At the same time, Skydio releases the Skydio 2 platform, and so the video that you've seen right at the beginning, which I still believe is the market's most advanced flying AI system. 2021, DARPA hold their Subterranean Grand Challenge finals. The winners are in this room. Brilliant job, of course. I mean, I guess this was definitely a challenge that pushed field robotics forward, and perception for sure. But still, the winner did not use any drones. They, from what I heard, they use the tactile feedback from the animals such that they're able to basically avoid the visual perception or vision-based perception as much as possible. 2023, Skydio released their X10 platform, which is a ramped-up version with thermal imaging, with flashlights to be able to see in the dark. But today, where do we stand? Do we have a drone or a team of drones that they're able to navigate autonomously and take decisions collaboratively on how to act in a challenging mission? And what is a challenging mission? So can we have construction site monitoring across different days? Can we have wildfire monitoring? I know many of us have been working in this area, so I'm not trying to shut down everything that exists, but I'm trying to show people how far away we really are from pushing a button and having something useful to this end. So what do we need to have a system like this that can help us in construction site monitoring or wildfire monitoring? I argue that first and foremost we need high fidelity SLAM. I know we sold SLAM about 1,000 times. I think Luca Carlone said that already in one of his speeches. And I think we need to solve it 1,000 more times. So high fidelity SLAM is still a problem. Which sensor to trust and when, and how to fuse all these sensing cues. So as I said, I've been working on vision myself, and have been trying to make the most of what vision can offer. But recently I heard a postdoc from Oxford, he has been working on LiDAR, so I'm exposing myself to the LiDAR world. And now you're looking at his suggested representation. This is really ongoing work about representing the surface geometry around each point using an ellipsoid. And then we classify these geometric primitives as lines, as planes, as balls. And this, what does this bring? This brings some scale agnosticism and some structure agnosticism, which in effect translates to robustness. So I remind you, this is visual odometry. This is no SLAM, so there's no loop closure. So now the sensor head just returned back to a position where it has been to before, with very, very small drift. So overall, this is, again, as I said, is ongoing work. So I'm just sharing sneak previews. So it's very stable. So this is now dynamic motion. You will see that he really tried to break it. So it's pretty stable. It has very good robustness in average odometry error. But I argue, so he will make it break in the end. So now it's in a narrow corridor, and later on you'll see how it breaks. But I'm hoping to see how we can fuse it with vision to disambiguate in different scenes or even dynamic scenes, basically. It takes a while to break, but we're almost there. So yeah, it's just going off in a narrow corridor. Yeah, here we go, it breaks. So let's say that you have your favorite sensors and you are able to make the most of your vision, of your LiDAR, of your IMU, of your event-based camera. So how to fuse all these sensing cues? And top performing SLAM systems are using a discrete set of motion estimates, basically from favorite sensors, to figure out how to approximate, essentially, how the sensor suite has been moving. So, of course, you can see the red lines there. They show how that this is an approximation to what really happens in reality. That's why it's discrete time SLAM. And in such cases, the syncing of the sensors becomes very important. And that's why you have expensive sensors out there doing the hardware synchronized version of sensor syncing. And in my lab, as well as in the wider literature, people have been working towards continuous time SLAM approaches. So basically to still approximate the trajectory, but with a continuous function. In this case, B-splines, so this was our first attempt. Continuous motion parameterization using B-splines and a non-linear least squares optimization using a sliding window. And what comes with that is asynchronous sensor sensing is supported for free. Then we were thinking, maybe we don't really need to optimize this monolithic window all the time. Maybe we can be selective on which parts of the trajectory to optimize. And what if we could assess which spline bases, which parts of this trajectory to modify based on their covariance estimates? And that's where we started looking into continuous time slam with Gaussian belief propagation-based optimization to offer a decentralized probabilistic inference and covariance estimation for free. So this is a problem that is close to my heart. I have been working on Gaussian belief propagation during my PhD, and it was very nice to come back to this. So it's very interesting to see how some of these notions are coming back. Still, I have to say, it's definitely not that we solved the problem. So we are still yet to see how well this system performs with respect to real data, right? So high fidelity SLAM, we've been experimenting with different sensors, deep learning, I didn't talk about this, place recognition, Toby will talk about it later, trajectory representations, this is splines, or there are people working in Gaussian processes. Why? Because we want to form this awareness of space for a robot, right? So the robot's pose and a map of the surroundings. And what's a key thing so far is that this map has been largely sparse. And this brings me to the second problem that we need to be dealing with. How can we create richer scene understanding for interaction and path planning? And most importantly, what makes a useful scene representation? And let me show you what I mean by that. So here is the goal. Let's try and reach the destination by minimizing the errors in the visual odometry, go from A to B. So we know that the straight line is the best path. But of course, we also know that maybe some parts in your scene are not really useful for your estimation error. So if there is wind and there are trees, maybe you can avoid looking at them, and maybe you can look at the buildings. And here's one example of a work that we worked towards that. This was semantics-aware emergency landing. So wherever you are, try and figure out a safe landing spot as soon as possible. So how we did that? We've used the RGB image and SLAM that's running on the background, a semantic mask out of a semantic segmentation network, and some depth understanding to train a deep reinforcement learning policy to choose one of a discrete set of possible motions that talk directly to the UAV's controller. And after many, 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 many failures and attempts and successes, we had successes. You can see one example on the left of a successful landing, and two examples of failure cases on the right, where on one side the vision is failing us, where there are no features on the lamppost, and in this case it's summer or winter in Zurich, I don't know, and the terrain is, the bushes are classified as terrain, they have the same color. So which shows us, oops, sorry, moved too fast, which show us really that there is a need for not only just good semantics, but maybe some ways of understanding how uncertain these semantics are. So yeah, being able to classify your scene is interesting. But there are cases, like in this case here, where we really want to do an extra bit of classification. So within one class, let's say the class of stones, we want to figure out the different stones, which is what we call instance segmentation. So figure out different stones from each other. And this is part of a bigger project together with other roboticists at ETH in Zurich, architects, mechanical engineers. And the task was to use visual LiDAR inertial sensing mounted on board an excavator that would autonomously scan the area for stones, select which stone to pick up, and place it in a way that it would create a stable wall. So in the first case, you showed, you've seen a 10-meter freestanding wall, and then by the end of this project, then we had 65-meter long wall being built. So the big problem there was, okay, in the beginning you can have all your stones scattered around and you can figure out what they look like, what their shapes look like, and then pick them up. But what if they are in a pile? And that was the bigger problem for us, right? So yes, you can classify them all as stones, but then we needed to do some labeling propagation to figure out the boundaries of these stones in order to help the excavator decide which stone to grasp and then try to show it again around, well, experience the different sides of it around the sensor head in order to build a vocabulary of different stones and figure out which one to pick and where to place it. Now, from scene understanding, then the next step that would really blow up what it is that we can do, so to really go towards this vision of having autonomous drones for wildfire monitoring, then what we need is multi-agent collaboration and coordination. So what information to share between agents and where to look for information in a scene. And I don't have a lot of material to show you here because this is more, we're working more on collaboration and not so much on coordination because I think we still have some big problems on multi-agent SLAM that I'm going to talk in a bit. But definitely, I think where to look for information in a highly dynamic scenario will be very interesting. So I showed you this video before, which was about centralized collaborative SLAM. And we were thinking, right, so what's next? So obviously, the biggest bottleneck here is that all data needs to pass through the server, so that's your bottleneck. So you cannot really have 20 drones all trying to send their information down to a ground station or up to a server. So we've been working towards distributed collaboration, and I think it's a very interesting topic to start exploring in order to enable stronger collaboration by having really combining these different viewpoints of information from different sensors. And again, just 2 slides on a sneak preview on some ongoing work about asynchronous distributed optimization. So here's a problem. You can see the poses of different robots. You can see their features that they are shared. And obviously, the best thing you can do is do the maximum a posteriori estimate of this problem. But if you want this to be done scalably, then you need to split that problem up into different problems, one for each robot. But then you know that somehow you need to make estimates converge. And this is where we, again, look into belief propagation to regulate the updates that we are sending to other robots in order to ensure consistency and avoid overconfidence. So just to show you one video of this working on the Freiburg dataset using, I think it's 5 different robots, having also some outliers being introduced there to show some robustness. So overall, I hope that I convinced you that with these 3 challenges, there is a lot to address in order to boost robotic perception and collaboration for robotics autonomy. And I think it would be very interesting to see in a few years' time how far along we are with respect to field robotics and robotic perception. Thank you very much.
We have time for one very quick question. Anybody in the audience? Josh, you want to come set up? And we'll flip on Josh's slides while we do that. We have Josh Mangelson coming up from BYU next. Questions? I have a question.
Yep.
So if we're thinking about sort of where the commercial space is, and I can go buy my Skydio drone, does all this cool stuff, I guess where is the gap between that and where sort of the research domain is, in the sense that should we be expecting the hardware to keep getting better at the same rate, or do we think we sort of hit an asymptote when it comes to what they're going to be able to do with SLAM and multi-agent coordination and all that?
So you mean what space of research there is with respect to what the industry can do today? Is
Yes.
that the question?
Yeah.
Yeah, that's a very good question. And I think that we're really coming, in many ways, we're overlapping. And that's why I really love to see people from Skydio actually coming to the conference and presenting. I saw there was someone, yes, on Monday. Yeah, I think that it's about, on one side, sticking to our roles, right? So our roles as academics to keep doing the things that are a bit riskier, maybe, for the companies. But also, I'm really, really I would love it if Skydio would come and say, here's our drone, break it. Here's our system, show us how else we could be doing these things. So, and this, I mean, I'm talking about Skydio, but I'm sure there are representatives of other companies here as well, which would be lovely to have as open an environment as possible for us also to keep helping, so it's a two-way process, right?
I love it.
Good.
Thank you so much. That's a call to you, drone companies. Come talk to Margarita. Thank you again.
Thanks.